Hello students, this video is designed to help you with Chapter 12. It's on regression inference. Remember in Chapter 3 we talked about making scatter plots and drawing lines of best fit or least squares regression lines through those scatter plots. In this chapter we talk about, is there really a linear relationship between these data, or is it just due to random chance? This chapter is designed to help you draw inferences on sets of data. Let's get right into it. Here's the first exercise. It talks about Old Faithful, a naturally occurring geyser in Yellowstone National Park. They called it Old Faithful because it erupted very faithfully, right on schedule, they said. Doesn't look like from every 44 to 125 minutes. Doesn't look like it's very faithful to me, but hey, I didn't name it that. You can see that in this scatter plot, they've drawn a least squares regression line through it, and you can see that there's a cluster of data down here, a cluster of data up here, but in general it does follow this linear pattern. It asks us to answer these questions for describing a scatter plot, approximating the equation. Take a few minutes to pause the video and answer these questions, and then come back to see if you did it right. All right, let's see how you did. You can see that I did a couple of drawings here. You're going to see that in a moment. The first question asks us to describe the scatter plot, and you can remember from Chapter 3, it was asking us to describe scatter plots in 4 different ways, in terms of its direction, its form, its strength, and whether there are any outliers. The direction is clearly a positive association. It looks like these values are varying at the same time as the x values go up, the y values go up. The form, these data follow linear form. That's to contrast it from a nonlinear form. That doesn't look like there's any curve here. It doesn't look like it's growing in an exponential way or in a logarithmic way, anything like that. And we can also include that there are 2 main clusters of data. That's not necessary to include, but certainly in form you can say whether there are clusters of data. You can see this cluster down here that's near a duration of 2 minutes, and this cluster up here which is near a duration of maybe 4.1 minutes, something like that. For strength, we say it's a moderate to strong association, as the points tend to be close to the LSR line. It looks like most of these points are pretty close. There are some that have a pretty high residual, like this point, for example, is a pretty high residual away from the LSR line. So does this one. But in general, I would say that most of these points are clumped pretty closely. So if you said moderate, if you said strong, either way, I wouldn't be upset about that. And we can actually measure that using the correlation coefficient, or R. For outliers, we say no apparent outliers because there's nothing that has an extreme x value or extreme y value or something that's both extreme x and y. It was asked for us to approximate the equation of the LSR line. We got y hat is equal to 44.10.53x. This seems pretty not approximate, but I'll tell you exactly how I got it. I found these 2 points here. I approximated those 2 points, and then I used my trusty slope formula, you remember from algebra, to find that. So if you wrote 10.5, that would have been okay. If you were somewhere in the 11 range or the 10 range, that wouldn't be a huge hassle because all we're asked to do is approximate the equation. So 44 was our y-intercept, and if you said 43, I think you would have been okay. Anytime you're writing the equation of a least squares regression line, you are required to include what the variables mean. For example, this is y hat. This is the predicted interval of time between eruptions. And you also have x, which is the duration in minutes. If you look back at the scatter plot, each of these points is an actual piece of data, like an actual eruption that actually happened. For example, this point represents an eruption that lasted for 2.9 minutes and had a maybe 79-minute gap in between it and the previous eruption. So this piece of data is an actual piece of data. This right here is not an actual piece of data. It's a predicted piece of data. In other words, it's a predicted y value. It's a predicted interval. So we can't say that the least squares regression line gives us y. We can say it gives us y hat, which is a predicted interval of time. We don't use x hat because we're saying, well, we know these values are going to be the independent variable. These values are going to be what we're going to be basing our predictions on. So for every observed x value, what's the predicted y value? That's why we use y hat and not x hat. If we were to take just a random sample of 20 eruptions, would we expect that LSR sample line to be similar? Well, it would probably be similar, but it probably wouldn't be very exact. Like, for example, if you took 20 points that were here in this cluster, you might only have points that are like this in a pattern that looks like this. So your LSR line might be much steeper and might have a much smaller y-intercept. Or, contrary-wise, we could have points that are only here. And it's possible during sampling to get points that aren't really representative of the population, especially when there's 222 observations in the entire population, and we're only looking at 20 eruptions. So not very representative of the 222 total eruptions. That's what we're looking for there. However, if you were to take 1,000 random samples of 20 eruptions, that's much more. You're cutting down on your sampling variability by just having much more samples and saying, well, it's possible that this observation is weird, that this sample is weird. It's possible that maybe 5 or 10 or 15 or 20 of them are weird. But if you take 1,000 random samples, the chances are that most of those samples are going to have LSR lines when you do the least squares regression for that sample. They're probably going to be pretty close to this line. And you can see down here, you can take a bunch of different samples of a bunch of different, a bunch of different samples of 20 eruptions, and it looks like these sample LSR lines are pretty similar, right? The slopes are a little bit different, the y-intercepts are a little bit different, but they're all within a certain range. They're all within a certain interval, you might say. That's a little foreshadowing. Taking the average of the slope, the y-intercept, and the standard deviation of all of these samples are going to give us a good idea of the parameters for these values, and that's a good springboard into the next page. On the next page, it's a description of the different symbols that we use. So when you're taking a sample and just looking at a sample and trying to find a least squares regression line, we use these symbols. We use y hat, we use A, and we use BX. This is the form that we see in our calculator, right? That linear regression, linreg 8. Y hat is the predicted mean y value for a given value of x. But for all 222 eruptions, we're looking for a population value. We're looking for the population least squares regression line. And once we're talking about a population LSR line, we're using different variables here. This variable we're using is mu instead of y hat. This is the mean y value for a given value of x. A, or in this case I should say alpha is the population y-intercept, and beta is the population slope. Now most of this chapter, a little foreshadowing for you here, most of this chapter is talking about how we can estimate this population slope using repeated sampling and finding a bunch of different sample slopes. If you look here, you can see 1,000 different samples, and you can see that it's starting to approximate this normal distribution, which should surprise absolutely none of you. This mean, if you notice, it's very close to 10.5. That's kind of what we calculated before. This mean represents the mean observation of all 1,000 different samples of n equals 20, which means it's probably pretty close to the parameter. And incidentally, when we find this mean, it is going to give us something that's very, very close to 10.5. The standard deviation of this sampling distribution is a little bit different than the sampling distribution standard deviations that we've had in the past, namely because of this. So this standard deviation of B, which is our slope, is equal to the standard deviation, the overall standard deviation, the one that we were looking at before, divided by the square root of n, which is a very familiar parameter, and that's multiplied by the standard deviation of the x values. Now, you might be wondering, why is this included in the formula here, and I'll try to explain it very simply. When you're talking about doing a linear regression, when you're talking about making a scatter plot like this, you want all of your x values to be pretty variable. You want a lot of different samples of a lot of different x's, so you get a good idea of what's going on over the course of the relationship. So the reason why this is here is because, well, if we have a large variability of x values, like a lot of different x values to choose from, that's going to be in the denominator, which means it's going to make this smaller. It's going to make this standard deviation smaller. We want more variability in our x values so that we have a lot of different x values so that the variability for our slope goes down. Hopefully that makes sense to you. And also, as you can clearly see, the sampling distribution of n is approximately normal. I want to talk briefly about regression inference because that was an idea that we talked about at the top of the video. What if I make this least squares regression line? Well, I know that I'm making this least squares regression line and it's passing through individual points, like this point here, this point here, this point here. And one of the requirements is that we can't do regression inference unless for each individual x value, the y values for that x value are normally distributed. So for example, for this x value, let's say it's the x value of 1, which means the duration of 1 minute. We need the y values to be normally distributed around that x value. Same thing with every other x value. The reason that it has to be normally distributed, well, is because we can't perform regression inference if they aren't. There are 5 different conditions for regression inference, and hopefully you should be able to see some sort of pattern here, some sort of mnemonic. I haven't been able to come up with anything, but hopefully you can figure out a mnemonic device to remember these conditions. The first condition is the form of the scatter plot must be linear. You can't have a curved scatter plot, or else, well, you can't perform regression inference on it, or you just can't, sorry. For I, it stands for independent. Either the individual observations have to be independent, or the number of samples, the number of individuals in your sample have to be less than or equal to 10% of the population. This is a familiar condition. Another one is normal, another familiar condition for any fixed x, the y value is distributed normally. That's what we have here. Or the residual histogram has no skew or outliers. If you look at the picture on the top of the video, the residual histogram is on the right-hand side. Equal standard deviation. For all the x values, the standard deviation of y should be equal, or the residual plot is equally variable. I'm going to show you what that means. You can take a look at the residual plot again at the top of the video to see whether it's equally variable. And finally, random. The sample is randomly selected for the population, or the treatments are randomized. Most of these are pretty familiar conditions. However, when you're doing regression inference, you must address all of them, every single one. Well, instead of the A, because the A stands for and. Taking a look back up here, we talked about, we talked about the equal standard deviations. The residual plot should be equally variable. And we talked about normal. The residual histogram has no skew or outliers. Well, here you go. Here's the residual histogram. It's got no skew or outliers. It doesn't have, a long extended tail here. It doesn't have a long extended tail here. It's not exactly normal, but we're not looking for exactly normal. And again, if you look at this residual plot, I don't have a residual plot with a lot of points down here that are very, very close to the line. And as you get further and further, you get farther and farther away. It doesn't have that cone shape. And you remember you seeing that cone shape in a previous chapter in chapter 3, but here, since the residuals are pretty evenly distributed, we feel safe in doing a regression inference. That was over here. Okay, that's the video for the first part of chapter 12 for regression inference. Hopefully that was helpful to you. Good luck studying.